Okay, so talking about complex solutions. So just now we were talking a little bit about the graphs of parabolas, okay? So you have actually three different options. A lot of times we were finding out that parabolas could have two x-intercepts. They could also have one x-intercept touching down. And when we have an x-intercept that occurs only one time, that point is also the vertex. Yes, that's a vertex and an x-intercept. Or we also have an option of this. And actually, you guys were getting some answers like this and you didn't even realize, but there could be no x-intercepts. What happens is when you use the quadratic formula to solve to find x, you get a negative number inside the radical, okay? Now, we were talking about before, when we were talking about radicals, here's the famous sort of joke about imaginary numbers. So you have pi and I hanging out talking to each other, of course, because they're best friends. And pi says to I, get real, and I says back to pi, be rational. And this is because I is not real, it's imaginary, and pi is irrational. So now when you see that joke, you can laugh at it, okay? So the equation x squared equals -1 has no real solution. Why is that? Because if I square -1, what do I get? 1. If I square 1, what do I get? 1. So I can't take the square root of a negative number. We've been talking about if I were to solve that and I took the square root, and that's what they're doing right here. If you imagine that you could solve the equation with the square root property by taking the square root, you would get x equals plus or minus the square root of -1. So we can't take the square root of -1. We call that not real. The principal root of this equation would then be square root of -1. In 1770, this is a famous mathematician, Leonard, we say Euler, and actually he has famous numbers named after him as well, E, defined numbers such as square root of -1, square root of -2, etc. as imaginary numbers. So now what we're designating, we're saying the square root of a -1 is denoted as I. And that's what we use for imaginary numbers. Imaginary numbers often appear in addition to real numbers. A number that contains a real part and an imaginary part is called a complex number. This name and the use of I was coined by Gauss in 1830. These are all famous mathematicians, Euler, Gauss. Using the properties of radicals, all imaginary numbers and complex numbers can be written in the form a plus bi. And you're going to go into this a lot more in depth when it comes to your Math 95. You're going to be looking at this a lot. So this is kind of like an intro to what you're going to be looking at in Math 95. Where a and b are both real numbers, this is referred to the standard form of a complex number. So write each of the following complex numbers in standard form. So here we notice that this is the same thing as the square root of -1 times the square root of 36. You know why I said 6. I know you know why I said 6. Why did I say 6? Bingo. So if we simplify this is a perfect square. This is 6. The square root of 36 is 6. The square root of -1 we say is I. So basically I have, instead of just I have 6i. If we were writing this in standard form, what number is A? I have the bi right here. B is 6. And what would be A? Well, there is no number there, right? So if you wanted to write this like this, you'd say 0 plus 6i, or just 6i. But if you wanted to identify what A and B are, there's no number that's being added, right? There's no rational number that's being added. So here I have -2 minus, how could we simplify this? Right. Square root of 5, right? because it would be times. So yeah, I should have written it out first. Here, I'll write it here. -2 minus, and then the square root of -1 times 5. That's where we get the I from. Okay. So essentially we're just taking the square root of -1 and we're turning it into an I, realizing that it's imaginary and it doesn't really exist. Yes. Okay. All right, let's go on to the next page. What do you think about this one? What would you do to simplify this? So we have the square root of -1 times the square root of 4 times the square root of 3. Why did I break 12 into 4 times 3? Yes, 4 is a perfect square. So then who could tell me what would you get if you simplified this whole thing? 2i times radical 3. Yes. Here's the 2, here's the I, and then radical 3 stays. Okay? How would you simplify this one? 4 plus, so we could split that up, right? 4 plus I, right? Because not times, yeah, times radical 6. Can radical 6 be simplified at all? No. So we're just getting used to taking that I out of there and getting used to, working with I. Okay, here, find all real and complex solutions to the following equations. So what would we want to do? What method, right here, solve each equation using the square root method? So we're actually going back to something we already learned in Chapter 8, which was the square root method. How do we solve this using the square root method? -4, because we want to isolate, right, the square root property. We're going to isolate x squared equals -4. Yes. We take the square root. Take the square root of both sides. So we get x equals plus or minus the square root of -4, which is plus or minus, yeah, or 2i, right? 2i. And don't forget we want plus or minus because we want all possible solutions. Simplify solutions as much as possible. Of course, you would write this then -2i, positive 2i, and you could also check it. Yes? Yes, exactly. Normally you said there's no real solutions. In all the other examples, when you had the square root of a negative, you said not real or no solution, right? Here now, because what's happening with x squared plus 4, x squared is a parabola, right, that lands at 0, 0. If we add 4, it's shifting it up 4. So it's actually not crossing the x-axis, which is the reason why we have that imaginary solution. Okay, what are we going to do with the next one? Let's use the square root property. So we're using the square root property there. And what do we need to do in order to use the square root property here? So all I'm saying is it's not crossing the x-axis. So when we solve any quadratic, we're technically, when we set it equal to 0, we're technically finding the x-intercepts. So when we get this, it means, oh, this parabola is not crossing the x-axis. So there really are no x-intercepts, right? Yeah. Yeah, so these are the solutions, but they're imaginary. Yeah. No, because it's not, it actually doesn't exist. Just like your imaginary friends, they're not real. That's a good question that I can't really answer right now. Okay. And then, yes. Oh, no, I didn't actually plug it in and check it. But if I were to plug it in and check it, I would go like this. Negative 2i squared plus 4 equals 0. Okay, now this is where we're going to get into a little bit of Math 95 territory, okay? Because what is negative 2 squared? 4. Negative 2 squared is 4. What is I squared? In order for this to be, yes, I squared is negative 1. 4 times negative 1, plus 4 equals 0. Negative 1 times 4 is negative 4 plus 4 equals 0. So the reason why, so if I square, look at I is equal to the square root of negative 1, right? What would happen if I squared that? You would get, actually, the squaring would just undo the square root. So I squared is equal to negative 1. That's what we have here, negative 1. Okay? Okay, so let's try the next one. How are we going to, I only checked one solution because if I check positive 2, it's going to be the same. Okay? That's the check down there. What am I going to get here when how would I solve for x there? Using the square root property. So because we have isolated the perfect square, we can use the, what can we do to undo the squaring here? Square root, right? Square root. X plus 2 equals plus or minus, what's the square root of negative 49? 7i. Right, because of that negative. Anytime you take the square root of a negative, you're going to get the I, right? What are we going to do to get x by itself? X equals, yes, subtract 2 from both sides, negative 2 plus or minus 7i, which you actually always have two answers here when you're doing this plus or minus. So the solution here would be negative 2 plus 7i and negative 2 minus 7i. Okay. For the checking, if we want to do the check, let's check just one of them. I'll check the negative one here. So if we plug that in, negative 2 minus 7i plus 2 squared, is it equal to negative 49? I forgot to put question marks here. Okay, we want to simplify inside the square first, right? If we're just checking here, so what would this simplify to? Is it negative? Yeah, negative 7i squared equals negative 49. And if I square this, I'm going to get, yep, 49 times negative 1 equals negative 49. So that's negative 49 equals negative 49. Okay, what about this one? What am I going to do here? I want to use the square root method for C. How do I solve? Yeah, well, first I would want to divide, right, by negative 2, because I don't want to have to divide by a radical. So I have x squared equals negative 50. And then I'm going to take the square root. We're using the square root property, so square root. X equals plus or minus square root of negative 50, which I love it. You're getting the square root of negative 1 times 25 times 2. Way to break it down. Excellent. Okay, and then what? Plus or minus 5i, and the only thing that stays in is the square root of 2. Okay, so use your set notation, plus or minus 5i times radical 2. I should show the check because that's the thing that people get confused about. So the check would look like this. So let's take the negative 1, 2, negative 2 times negative 5i times radical 2 squared. Sorry I wrote that all wonky. I was trying to fit it in because I want to be able to have room for d. So we're going to square everything, right? Squaring 5, negative 2 times square 5, that's square negative 5, that's 25, right? Square I, negative 1, square the square root of 2, and that's 2. So now I have negative 2 times negative 50. You see where I'm getting negative 50 from? Negative 2 times negative 50 is 100, and that's what we wanted to see. This equals 100. Okay? What should we do for this one here using the square root property? What would you do? Yes? Okay. So it's because the thing is that the square root of a negative 1 doesn't exist actually. So that's why we're calling it an imaginary number, because before we said it wasn't real. So otherwise really we don't have, when you look at the graph, you're not going to see these solutions. You're going to see that all of these are going to not hit the x-axis. So that's where the I is coming in, because what I allows us to do is to continue to do the math. And it is used for practical applications. It's beyond my... Yeah, I does imply a square root of a negative 1. Right, because it's not the same thing, right? Because negative 1 is not the same thing as a square root of negative 1. Yes. Okay, so what about this one? How will we solve here? Square root. Yeah, we want a square root first because we have that square there. So we have 2x plus 1 equals plus or minus the square root of negative 12. And I like how you're breaking that down. So 2x plus 1 equals plus or minus. And yep, negative 4 times 3. So that's going to be 2i times radical 3, right? 2i times radical 3. Does everybody see where I got that? The 2 coming out from the 4, the negative 1 coming out as an I. And then what do we do to get x by itself? Subtract 1. Okay, 2x equals negative 1 plus or minus 2i times radical 3. Divide by 2. X equals negative 1 plus or minus 2i square root of 3 divided by 2. That's what your answer will look like if you do the quadratic formula, right? So if you did the quadratic formula and yeah, if you actually FOILed this out and then you tried to factor, it wouldn't be factorable. Instead, you would have to use the quadratic formula. So this is what it would look like. Negative 1 plus or minus 2i radical 3 over 2 in set notation. And if you plug it in, it's actually not that bad because the 2 divides by the 2, right? Cancel. Then 1 minus 1, and then you're basically squaring that again. I just don't have a lot of space, and we need to move on to the quadratic formula. So the last bit is all about the quadratic formula. Find all real and complex solutions to the following equations. Solve each equation using the quadratic formula. Simplify as much as possible. Okay, to get this one set up, this one is already set up to use the quadratic formula, right? How do you know that? A is equal, yes, because it's equal to 0. So A equals 5, B equals 6, C equals 2. But this one is not set up yet to use the quadratic formula. What am I going to need to do to set it up? I'm going to have to, in order to add 2, I'm going to have to first FOIL, because I can't add the 2, it can't get into those parentheses, right? Until it's FOILed out. So 2x squared minus 4x minus x plus 2 equals negative 2. Now we add 2, right? 2x squared minus 5x plus 4 equals 0. Do we all get that? Did I do it right? Okay, tell me your A, B, and C. A equals, B equals, and C equals. So we have x equals negative 5, which is 5 plus or minus square root b squared. If I square negative 5, what am I going to get? Positive 25. So this b right here will always be positive. The b will. Yes? I'm setting it equal to 0 here. Set to 0. Right? So we can put it into standard form. Does that make sense? Minus 4 times a, which is 2, c, which is 4, all over 2 times what? 2. Okay. Now, let's simplify even further. Equals 5 plus or minus square root 25 minus what? 32 over 4 equals 5 plus or minus, what's 25 minus 32? Negative 7 over 4. So let's use our complex numbers here. 5 plus or minus, yep, square root of 7 over 4. That's as simple as it gets, okay? Let's look at, so this is our solution then. 5 plus or minus I times radical 7 over 4. Okay, one more and then call it good for today. Okay, so that's the solution there. This one, x equals, tell me what to write. All over 10, yes. So negative 6 plus or minus the square root 36 minus, now notice that number is probably going to be bigger than 36, so that's why you end up with a negative. 20 times 2 is 40 over 10 equals negative 6 plus or minus the square root of negative 4 over 10 equals negative 6 plus or minus, okay, how many i's? 2i. Why 2i? Square root of 4, right. 10. Now, this came up before. Can this reduce? Can you reduce this? What number goes into, the number has to go into all three because 10 is dividing into both. Negative 3 plus or minus I over 5 because everything divided by 2, right? We reduced by 2 over 2. That's why. Okay, so this is the solution here. 3 plus or minus I over 5. Okay. So this just came from here. So negative 7 was our number, right? So I comes from the fact that we have a negative inside the radical, and the 7 just stays because 7 is not a perfect square. Okay. Oh.